Hi everyone. So in this video we discuss how the gradient is computed, especially in networks where you have hidden-to-hidden recurrence. And the main mechanism that we'll discuss is called back propagation through time, and the abbreviation is BPTT. So basically we are concerned with a situation that looks like this. So you have an input, and then the input goes to the hidden layer, and then you have an output. This is at every time step. And then you have a hidden-to-hidden recurrence, so there is one time step delay, and there is a connection from the hidden layer at time t to the hidden layer at time t plus 1. And you could imagine how the computational graph is unfolded through time. So you would have versions or copies of this graph, but then this connection will unfold into horizontal connections going through time from h1 to h2 to h3 and so on. So now these connections have weight parameters that remain constant through time, meaning that the weight parameters defined by W are the same weight parameters that go from H1 to H2 as the ones that go from H2 to H3 as the ones that go from HT to HT plus 1 in general. So you could imagine that in forward propagation, these weight parameters get raised to a power that becomes as large as the sequence length. So if the sequence length is 100, then the weight parameters, so there is you have h of 1 multiplied by w to get h of 2, and then multiplied by w again to get h of 3, and so on. So there is this exponentiation or raising w to a power up to 100 at the end of the sequence. Now the same thing happens in backward propagation, right? And that's what we will see in this video, is that basically the gradient of the cost with respect to the early hidden layers will have the values of w raised by powers proportional to the sequence length. And that could be problematic from an optimization standpoint, because that could facilitate either explosion or vanishing, or so exploding gradient or the vanishing gradient phenomena based on whether the values of W are less than 1 in magnitude or bigger than 1. So let's consider, to get a more precise feeling of that phenomenon, let's consider computing the gradient of the loss function with respect to W, right here. So the same weight parameter could affect multiple hidden units, right? So we sum over I, where I here the index of the hidden unit, and it's also affecting hidden units in all the time steps. So we sum over T, where T is the index of the time step. So for every time step, we sum over the time steps, and then for every time step, we sum over the hidden units that the weight parameter affects, right? So, and then for every one of these, we compute the gradient, right, or the Jacobian, the partial derivative of the loss, with respect to every hidden unit hi at time step t, and we denote it by hi of t, right? So this is the partial derivative of the loss function with respect to hi of t times the gradient of w with respect to hi of t. Right? So over all hidden units in all time steps, I compute the derivative of the loss with respect to that hidden unit times, right? Because this is the chain rule for backpropagation, times the gradient of this hidden unit with respect to W. And just for ease of notation, we are calling W of t a copy of W that's used only at time step t. So when you unfold the computation graph, we call W of 1 the version of W at time step 1, but they are all identical copies. W of 2, the version of W used in the second time step, and so on. Now note the following, that in order to compute the gradient of the loss with respect to the hidden unit vector at time step t, so these elements right here, right? In order to compute the vector of these elements, you need to do what? So the hidden layer, so if I unfold the computational graph, right? So this is h of t, right? That right here is h of t. And then I have t plus 1, right? And that right here is h of t plus 1, right? Plus 1. and I have W going from h of t to h of t plus 1. Then the cost, how is h of t right here affecting the final output? It's affecting O of t, right? So it's affecting the output right here, right? And it's affecting h of t plus 1, which by itself will affect the final output through its contribution to O of t plus 1 and its contribution to h of t plus 2. So when I compute the gradient of the loss is computed based on the outputs, right? With respect to h of t, I need to compute through these two paths. One path coming backwards from h of t plus 1 and one path coming backwards from O of t, right? So the one coming from O of t is right here. So basically you have the Jacobian of O of t as a vector with respect to h of t as a vector, right? Times the gradient of the loss as a scalar with respect to O of t as a vector, right? So that gives the path of the gradient of the loss with respect to h of t that's coming backwards here through O of t, right? Plus the path that's coming through or coming backward through h of t plus 1, basically containing the Jacobian of h of t plus 1 as a vector with respect to h of t as a vector times the gradient of the loss with respect to h of t plus 1. Now, if I want to compute the Jacobian of h of t plus 1 with respect to h of t, here we take an example. So in this part right here, we take an example of the hyperbolic tangent nonlinear activation, which is a common activation used in recurrent neural networks, and it is common in recurrent neural networks for the specific reason of avoiding the vanishing and exploding gradients because the weight parameters get raised by high power, right? So the Jacobian, if the nonlinear activation in every hidden unit is the hyperbolic tangent, then the Jacobian of ht plus 1 with respect to h of t will be given by the W transpose times a diagonal matrix whose elements are 1 minus the corresponding element of h of t plus 1 square, right? So the first element is 1 minus h1 of t plus 1 square. Second diagonal element 1 minus h2 of t plus 1 square, and so on, right? So every time I compute the Jacobian of h of t plus 1 with respect to h of t, I have multiplication by the weights, right? So note here that this multiplication will result in raising W to a power when computing the gradient of the loss with respect to earlier hidden layers, right? Because every time I back propagate, I have a multiplication by W, right? Because this is the Jacobian of h of t plus 1 with respect to h of t. But when I compute the gradient of the loss with respect to h of t plus 1, right? So here this is the gradient of h of t with of the loss with respect to h of t. When I compute it with respect to h of t plus 1, I will have the Jacobian of h of t plus 2 with respect to h of t plus 1. And that will have a multiplication by W again, right? So if I am at an early time step in the sequence, and I compute the gradient of the loss with respect to that early time step with the hidden layer activation, that early time step, I have a large W raised by a large power contributing to the gradient. And the reason is very simple. If I am very early, I affect the loss through multiple connections, through the direct connection to the output at the current time step, and through the connection to the next hidden layer. But that connection to the next hidden layer affects a lot of outputs, right? So a hidden layer activation in the first step, in the first time step, will affect the outputs in all the time steps in the sequence, right? And that's basically, I hope this made you appreciate how not only in forward propagation, but also in back propagation of training of recurrent neural networks that have hidden-to-hidden connection, how there is a raising of the same weight parameter to a power, and that could give rise to problematic issues in optimization like the exploding and vanishing gradients. Sounds good? Thank you.